Hello, everyone. My name is Sandeep. I'm the field CTO at Hasura, and I'll kind of be the MC or rubber duck for this webinar. I'll kind of be your representative. I'll kind of follow along the webinar and keep asking questions, keep doubling down on some of the points, especially if I don't understand them. If you have any questions, please feel free to pop them in the chat, and I'll make sure that I'm keeping a tab of them, and I can ask our speaker today to kind of answer these questions or to double click on any of the points he's made. And speaking of the speaker, Praveen, do you want to introduce yourself and kick off the webinar?
Yeah. Hey, folks. Welcome to the webinar. So I am Praveen. I work as a staff developer advocate at Hasura, and I've been working with GraphQL for a few years now, and specifically on the stack side, pretty much a lot of Node.js code, a lot of JavaScript code as well. So a little bit of understanding of how the tooling has evolved over the years, both across GraphQL and also in the API space. So pretty great to present this one.
That's amazing. And what's Praveen not saying is that he also works with the GraphQL Foundation and a lot of specification related stuff, a lot of activities related stuff too. So it'll be great to kind of get a sense of the activities in the foundation too.
Yeah, awesome. So, so the agenda for today, right? We're looking at the state of GraphQL tooling in Node.js. But before that, stepping back into seeing what are the benefits of GraphQL and why was it easy to consume, but it's actually hard to create and expose, right? Looking at this evolution of tooling, right? And why GraphQL was introduced and how it became pretty easy to consume for front-end developers. The features of GraphQL spec and also how it actually evolved was to consume it easily, because you can now ask for exactly what you want and make multiple calls to your DB in the backend, but then consume it in a single query on the client and whatnot, right? So all of the benefits are actually abstracted from the backend, and they just delegated to the front end. So the clients and the front end developers felt empowered to be a full stack developer, where they're able to now not worry about what's happening in the backend, but then just start asking for a lot of things to the GraphQL interface, right? But then the moment they actually try to extend this problem to creating the GraphQL server themselves, rather than actually asking the backend folks to do it, that's when the problem starts, right? The problem starts when you're starting to create and expose. So you have a bunch of existing services. You have a database, you have a bunch of existing REST APIs, which just talks to the DB and gives back some JSON, right? Now, front-end developers have understood the benefits of GraphQL, so they want a GraphQL API, right, on top of this existing service, which talks to the DB internally. So how do you go about this problem statement, right? You start by implementing a pretty naive GraphQL solution on the backend, and with Node.js or probably with any other GraphQL server tooling. What you'll probably typically do is you write a bunch of type definitions for your schema. You write a GraphQL schema, and you write a GraphQL resolver, right? So you have a schema and you have a resolver which maps to that schema, and you write some logic within that resolver which gives you back some data. For something which has existing services, where you have existing REST APIs like get authors, get articles, and whatnot, which talk to the DB, you write something like a GraphQL proxy, because technically you're just reusing the REST API that's already there, and writing a resolver proxy on top of the REST API. And that could also be new code on top of these existing REST APIs, which will talk to the DB. So you might write more GraphQL schema definitions, and you'll write more resolver code on top of this, right? So a combination of a proxy to your existing services and a combination of like new resolver code that we'll be writing. Like
So I
now,
have a
let's
question about the previous one, right? So
yeah.
the previous slide where you're adding new code, new resolvers. So is this like the glue code to take, let's say, your existing endpoints like get author, get articles, and either do the glue part in the GraphQL layer in my
Yeah.
resolvers. I kind of, if I don't have access to the underlying database, or if I can't expect my backend engineers to build a new endpoint for me, am I writing the glue code in my resolvers?
Yeah,
That's one
that's right.
option. And is the other option to have a new endpoint build and then use that, which can actually do the gluing in the backend itself?
Yeah.
Is that what I'm doing?
Yeah. So there are a couple of options here, right? So whether you're reusing an existing API or you want to like avoid or skip that REST endpoint and then write your own GraphQL from scratch. When you're reusing the API, you're writing a simpler proxy, which
Mhm.
is does a proxy to that REST API, which already has the logic to fetch data from the DB. So you don't rewrite that logic in GraphQL. But let's say you're skipping that REST API and you want to write a GraphQL native resolver where the logic of connecting to the DB, if you have access to the DB, by the way,
Right.
where you will write the resolver logic within the GraphQL layer. So there are two approaches here. So a simple proxy and like a very detailed connection to the DB and performs the actual queries for you. Yeah. But in
Understood.
both the
Understood. I
cases,
think
there's a
that
lot
there's
of
a
boilerplate code that you'll be writing, which we'll come back to.
Yeah, that's exactly what I was going to say. I think two things jump out here. One is it sounds to me like if I need to iterate on a feature, like every sprint, my product manager comes to me and I'm one of the engineers in this equation, let's say, um, maybe in charge of the GraphQL layer. Uh, every product iteration, I will need to think about, can I reuse existing REST endpoints? If so, can I include some, uh, let's say, pass-through glue code or whatever? Or I need to write some more nuanced resolvers which can talk to the DB. But that seems like a way of life every iteration, right? So
Yeah.
the benefits of like a self-serve platform that the front-end engineers would get, I don't kind of get that. For me, the drudgery continues every iteration, is what you're saying. Okay, cool. So that's one. And the other important thing that you just mentioned is the access to the underlying database. Right now, depending on the size of the organization, I may or may not have access to the underlying database. So sometimes I might just have no other option but to play with the existing REST endpoints and see what I can do, write some bad glue code. For example, here in our example, we have get authors and articles, which I assume is getting that relational data, right? Like the
Right.
all of
Mhm.
the optimizations are kind of included there. But if I
Right.
don't have access to the DB, I might just have to make these two queries naively and then do a join in my GraphQL layer.
Yeah.
So, which can have a lot of implications, right? I'm guessing the performance is not going to be pretty great to write home about, but it's also a cadence or rather like a velocity question. If I don't have access to the underlying database, maybe I need to request the backend engineers when they have the bandwidth to take up my REST endpoint, then they will have a performant implementation and so on. So all in all, it sounds like the problem of reducing iterations is not going away by this solution. And I'm guessing that's why you're calling it naive. But yeah.
Yeah. Yeah. And we'll go over into the optimization cycles, right? But I think to sum it up, I think as clients, as front-end developers do not have direct access to databases in most cases, they end up incrementally adopting this solution by just writing a proxy to begin with. And then probably once they get the backend folks to start writing a native GraphQL server, they'll have probably an optimized version of this solution, which will come in the next few slides. So,
All right. All right.
um, cool. So now let's look at the naive GraphQL resolver, right? Why do we call this a naive implementation? So you have like a schema which you've defined for, and in this case, for example, let's have patients, and each patient is attached to a bed, and a bed has a code and some more attributes, right? Now, how do you implement this resolver? Like you have a query, you have you have a resolver which will resolve patients, which is the top level, and then you need to return the name of the patient and the bed that they attach to. And so what you will do is typically you'll write a resolver for patients, and you'll write a resolver for the bed, which is a nested query. If you look at this, right? So you have these two different functions, and internally this would do an ORM query to actually fetch the detail from database. For example, that could be like a select name from patients table that will happen here, and here that would be like a select code from the bed table where patient ID is equal to something, right? So you will have this two naive function implementations, which are called resolvers in the GraphQL context. So this is the very simplest form of implementing this when you get started. But there is, of course, you can already see the problem here, like as the number of levels of nesting increases, you will start implementing individual functions for all of these, and there's a lot of well-played code. But creating more code is one part of the problem, but then there's also like a performance implication around this, right? Which brings me to the n+1 query problem, which is the dreaded problem in GraphQL, right? Looking at that patient's query, right? You have one query for patients that you make. It could be a select query on your database, and you have n queries for each patient, n queries for the bed query. So what's happening here is, yeah, of course, you make patients query, and then you're also like doing for each patient, you're iterating over the bed query n times. So you have this n+1 queries that you make typically, right? So for example, if there are 10 patients in your database, you're making 11 queries to get this data from the database in a naive implementation, which of course is not the greatest of performance implications, right? So if you look at 11 select queries being hit to the database, and this is for one user, and imagine this multiplied for a number of users to your database. So this is a very fundamental problem that you need to solve when you start your GraphQL server journey. And as you see, as the number of nested relationships increases, the depth of your query increases, the problem becomes exponential, right? If you look at this example of author and articles, and for each article there is a tag, now it becomes not just an n+1 problem, it becomes an n+1 plus n plus n square, where for each article you fetch a tag, and for each author you fetch an article, and so on. So as the depth increases, it becomes an exponential problem. And at that point, your performance is definitely not going to be optimal, right? And there are solutions to address this problem. And I think the popular reference implementation in Node.js is the data loader approach, which Facebook had released. And this is a simple library to do batching. And what data loader does is it basically accepts an argument, and it's basically like where you're saying, if you go back to this example, instead of making n queries for each of these, for each author, for each articles, and for each tag, what you're saying is, hey, fetch me authors in one shot, fetch me all the addresses in one shot for the author, fetch me all the articles for all the authors in one shot. So you're making one exact query for each of the nested levels. So you'll probably be making, instead of 1 plus n plus n plus n square, you'll be probably making 4 independent SQL queries, right? And the way you can do this is by implementing a data loader approach, where you have a loader which accepts an argument of like an array of IDs that you can pass in. For example, when you're fetching addresses for an author, you will have an array of authors that you want to fetch the addresses for. And you will make a select query which will have a var clause which says in this list of authors, right? And then and you will get all of those responses. So you will have 4 such SQL responses to process, and you will have to do the stitching of data internally to return back to the client, because the client has asked for like 4 levels of nesting, right? So you will have to do that data stitching here. So that's one approach. The other approach is, of course, a generic batching solution. Data loader again is one form of batching approach anyway. The other way to look at is, if it's not just a database that you're talking to, can the REST API that you're talking to have a batch endpoint, right? For example, if your existing REST endpoint has authors and articles, is there a batch endpoint that I can define, which will give me both articles and authors in a single REST endpoint, right? Now, this requires that REST endpoint to be implemented or newly implemented or either already existing in that API layer, so that I can call that batch endpoint in my resolver code, right? So here, for example, we're looking at fetching posts, and if you look at this, you're just making you're getting the post in one shot. So for you're getting a bunch of IDs that you're iterating over, and then for each user's ID, you're getting the post in one batched query. Now, this could be a database query. Yes, we are simulating a batch database query here. It could be like a SQL query that you make, or it could be like a REST endpoint, which handles this batch query already for you, right? In both the cases, I mean, the first case of the database query, you're writing a slightly optimal database query, which is to say, hey, instead of executing hundreds of transactions into your database, batch them into a single call and then make a query. In the second option, you're saying, let the REST API handle that for me. Let it do the SQL batching, let it do the optimal SQL for me, and let my GraphQL resolver actually call the REST API, which has the batch endpoint for me. So there are both ways to do this, right? And the tricky bits are, how do you now stitch this response back into the JSON format that your client is expecting you to return? So that's one of the other challenges in looking at batching, right? So yeah, so to recap, I think we've looked at a couple of options to implement a naive solution and how to optimize that naive solution with data loader and batching. And this is typical Node.js code that you would be writing irrespective of the framework that you use, more or less pretty similar conceptually. So this is what it looks like for like one particular resolver, and you need to replicate this for different resolvers, right? Now, going back to the API journey problem statement, like you have like a bunch of existing services, you want to expose a GraphQL API. We've implemented the naive solution by looking at resolvers and schema type definitions and a couple of options around that. So what's a
This
smart
makes
solution
sense.
here? Yes, Sandy.
No, I think I think the naive solution now makes a lot more sense, because I know why you were having to write that new code, right? For get articles and authors. I'm guessing that's like the batching implementation for you to avoid like a little bit of a problem.
Right.
Yeah, instead of doing that gluing. Okay, got it.
Yeah. So now, this is still probably not the best solution yet, right? Because you're still making like 4 independent queries to the database for that 4 levels of nesting that we talked about. And this keeps increasing as you keep increasing the number of queries, and it's all multiplied by the number of users requesting these queries to your database. So how can we be smart about this, right? If we look at the query, go back to this query, sorry. If I look at this query, and if you ask me to write a SQL for this, I would probably write a single SQL which does a join across this, and I'll give you this back, right? This could be like a select with joins across these tables with a couple of add classes involved and whatnot. So this is how I probably will approach this if I'm namely like looking at this problem statement. So the smart solution is like, instead of executing independent SQL queries, how about actually like compiling this query into a single SQL query and executing it in one shot? So why should I even make 4 different queries instead of making a single query, right? And then the problem here is the way GraphQL servers are designed to do it, right? The resolver approach typically is designed to make you actually resolve something on every level of every node that you're resolving to. So for example, the articles and authors, or the patient and bed problem, right? In both the cases, you're actually like resolving one node at a time. So if you're traversing through those nodes, you are actually like forced, or yeah, you have to return some data at each layer, and then it goes back to the other layer. So the traversal ensures that you're actually generating these many queries, right? Now, looking at the data loader approach, what if instead of actually like executing 4 SQL statements into the DB, what if we aggregated all of those SQL into one SQL statement and then doing an execution in one shot rather than doing 4 executions for that 4 levels of nesting, all right? What if we actually do just one execution, right? So that's a smarter solution to look at. Now, the problem, of course, is the way GraphQL servers are implemented and designed, that this is not easy to reason about and easy to implement or think about, right? Because you're just naively resolving to data. So the ideal solution is, of course, something which takes an incoming GraphQL, compiles it into SQL, which is an optimal SQL, speaks to the DB in one shot, returns back the data in one shot, right? That seems to be like a good ideal solution to reduce the number of hits to the database and also to get an optimal JSON data back from the DB. So that brings me to the compiler approach to addressing that performance problem, which is like to say, hey, data loader, having looked at it, it does traversal and it doesn't exploit joins. So you'll not be able to like generate a join query technically. There are like 4 levels of nesting and whatnot. So convert an existing GraphQL query into a single SQL query and get it done, right? What you can also do with this approach is you can leverage database specific features. Like Postgres has JSON aggregations, MongoDB has aggregate pipelines and whatnot. So depending on the database, the compiled SQL or the compiled NoSQL query can actually be optimized for the database that you are executing against, as opposed to an ORM, which is just naively executing a number of transactions into your DB. Right. So this is a similar example where you have the patient's name and bed, and you were just doing a select patient.name from, and then there is a where clause, join it across. So that just implementing this and expanding this to like a larger query, you can get the picture, right? So, so what's the tooling right now in Node.js? Yeah.
Praveen, I have a question.
Yeah.
So you said that this compiler approach kind of works from a performance perspective, right? That I don't need to run 1 plus n plus n plus n square queries now. I can run one query against the database, and it's one call as opposed to the number that we just discussed. It's as many calls to the database as well. It's super performant. But the other benefit I'm seeing is if I somehow implement this compiler approach once in a good way, remember those product manager breathing down my neck about every feature iteration problem that we were talking about? Does that go away too? Is it mostly a performance problem or also a time to market solution?
It is both actually. Yeah. Think about it, right? Once you write this compiler of sorts, which like essentially converts your GraphQL to SQL, and like SQL, which is probably like compatible for a particular database, Postgres, MySQL, or Oracle, whatever, right? It's a one-time implementation of sorts because you're essentially like writing a compiler which will just work for any other use case in your organization. So if you're using Postgres, and if multiple teams are using Postgres or the same database across the teams, a compiler which is written once can just be plugged into another database within the organization, and that the other team doesn't need to rewrite the GraphQL server themselves, because essentially what the compiler is doing is just converting GraphQL to SQL, and that's it's a one-time job. Having said that, it's not as easy to implement a compiler as well, because you then have to like look at all the permutations and combinations of traversing through the nodes, and actually generating a high performance SQL. Because sometimes a simple SQL join might not be really highly performant, as opposed to like executing 5 or 6 SQL queries independently, which is where leveraging database specific stuff like implementing JSON aggregations as part of a query, because then that will skip the back and forth between your database response and converting it into JSON. If Postgres already gives you back JSON, so use that. So you actually hit the database, get the JSON directly, and then just pipe it to the client, as opposed to you processing some database response from an ORM and converting into JSON structure that the client is requesting and whatnot. So again, yeah, compiler approach is great. It's again hard to implement, right? You need to like look at the nuances here. Yeah, and then now moving on to the tooling that's available today, specifically just looking at Node.js, right? How can you do resolver approach with the data loader and batching techniques that we talked about? Apollo server exists, GraphQL Yoga is there, there's type GraphQL, which is a pure TypeScript implementation. You can add TypeScript on top of the other two tools as well. There's probably more tooling, there's probably more reference implementations as well for doing GraphQL with resolvers. And this is purely just Node.js, and of course, this will expand if you expand languages here. What are the compiler approaches here? Hasura does compiler based approach for database queries. PostgreSQL does just this for Postgres. There's Tuckle, which does this for SQLite, and there are probably more tools that have been mentioned here, which takes in a GraphQL query, compiles it into an optimal SQL or a database query. Even there's probably a solution for Mongo, which exists. You should just convert it into Mongo query in one shot, right? Instead of doing the naive resolver and then applying batching techniques to optimize for performance, right? So this is server tooling landscape today, right? So what if you actually didn't need to even write these schema definitions and also the resolver code for GraphQL, right? Essentially, when you're writing a compiler, you're actually like you're basically like creating a SQL statement or your database query essentially, right? And it can't be customized for a specific set of schema definition that you have in your DB. It has to be slightly more generic so that it can be reusable for your other teams, right? And what if you also didn't need to like optimize for this N+1 problem, batching requests, where the compiler approach will obviously solve this problem, right? This is where Hasura basically comes in. So Hasura is a metadata-driven GraphQL engine, essentially a compiler, takes in your GraphQL and gives back a high-performance DB query for you. It also does something smart about authorization, where if a particular role-based user is querying the DB, it will also predicate push down the user role data into the database query. So for example, if I'm making a query as a user, the user's ID is actually filtered within the SQL statement that is getting compiled and then executed against the DB, as opposed to like getting some data and then filtering it on the server side based on the security tools. So again, leverages the database, gets the performance from the database and gives you the best optimal solution. Of course, and Hasura is open source. It's on GitHub for you to try out, right? Sari, do you want to also like talk about the architecture, about how Hasura fits in this
I
whole
was
landscape?
I I I would love to. I think Praveen, just from a time check perspective,
Yeah,
we have 20 minutes, so would love
yeah,
to maybe come back to this.
right.
The TLDR of this, folks, is that Hasura can help generate a subgraph over data sources. You can also kind of federate over these subgraphs using any tooling of your choice. If you're using Apollo Router, GraphQL Mesh, or even Hasura, you can find a way to kind of federate over the subgraphs. You can use these tools in conjunction with each other and so on to build what is a unified federated GraphQL API. Lots of benefits to being able to do that. Imagine the benefits of GraphQL spread across all of the data sources in your organization. So that's a Supergraph or GraphQL Federation promise. We'll get back to this. I want to make sure that you folks have more time to check out the performance numbers and the benchmark. So Praveen, I'll throw this back
Yeah,
to you.
pretty quick, right? So we have done some benchmarks against multiple databases and different solutions. This one probably, so the benchmark against Oracle, we've done this for Postgres, and I'll link it to you on chat as well. But the idea is that beyond a particular number of concurrent connections, Hasura can just scale really well for the same CPU and RAM, whereas Apollo, in this case, for example, for a pretty simple query, it's actually requiring 9x more nodes and resources for you to execute the same amount of queries and handle the same amount of concurrent connections. I've linked them to the blog post. I'll also link it on chat, right? And for a nested query, it becomes even more visible, where for a slightly large payload size with a relational query, which is like 2-3 levels of nesting, the query performance just stops for DIY GraphQL servers like Apollo, whereas Hustle just keeps going and is able to handle the request, right? So again, I'll link the
Praveen, is
GitHub
all
repo
of
as
this
well.
on the Oracle database?
Yeah,
So
this is
the data source is Oracle. You have a subgraphs using a compiler approach versus, let's say, the naive approach plus performance optimization. And you've tested this across multiple
yeah,
degrees of depth, I think, and it's testing the throughput. So the
yeah.
previous slide was more the latency, and this slide is throughput. Is that what we are checking?
Yeah, and also to correct you, I think probably I wouldn't call this a naive implementation on GraphQL servers.
Okay,
The Apollo server, I mean, that's probably the best optimization you could probably do when writing your
understood.
own GraphQL server, as opposed to again the
Understood.
compiler approach that Hasura gives you. So yeah,
Understood. Okay,
um,
got it. And we're testing the throughput, is it? Is that what the
yeah,
numbers are?
right,
On
right,
same infrastructure. So both
yeah,
sets of subgraphs are on same infrastructure. Uh, we use K6 or something of that
we
sort
do. Yeah,
to
we have K6. Yeah,
um, understood. And there is a repo where we can actually test this out. Okay, all right.
yeah,
Folks will share this in the chat as well.
yeah.
But there is a repo where these numbers are available. If you want to run your own benchmarks and submit PRs to that repo or create issues, please feel free to do that.
Yeah.
Praveen and team are constantly checking that out.
Cool. We also have a Postgres benchmark that I'll again share it in chat. But in the interest of time, let's actually dive into a very quick demo.
Praveen, while
Um,
you share your screen, we have a question
yeah,
on chat. I'll take that. Please continue
sure.
switching your screen
Yeah,
out.
yeah,
Dave has a question for us. In this compiler technique, where does the business logic live? Example, if the resolver should only result in active patients or only patients that belong to the user's department. Excellent question, Dave. So the compiler approach, I'll answer this on Praveen's behalf, works really well for the CRUD aspects of your API. So if you need to implement business logic, you can choose to implement it how you would normally implement in code or in the database. You can have a special query that takes in an argument to indicate whether, like a binary flag, a Boolean flag to indicate whether the patient is active or not. Or what you could write is also like a simple function that implements this business logic and in turn can call the CRUD APIs if needed. In the example that you've given, it's likely that you will have to write a function in the database or in like Node.js to query the database with this particular flag enabled. Um, you can actually write that logic in a function and add it to the graph in Hasura. The other way is if you check out the demo that Praveen is about to show you, the graph itself, if it does the CRUD API generation in a rich way, you will get these Boolean filter parameters in your API. So it's very easy for your front end to be able to pass this where clause actively. But unless if you want to enforce that as a business logic in the backend, you might have to write a function that does this kind of validation before you send data back to the front end. I hope that answers the question. We're happy to get into more detail as a follow-up if that works. All right, Praveen, back to you.
Cool. Yeah, thanks, Andy. But I'm going to quickly create a new project on Hasura Cloud. And again, this is all, you can repeat this with your Docker Compose setup locally as well. I think should work. So yeah, I have a quick graph empty project right now. What I'm going to do is I'm going to connect it to a Postgres database. I have a read-only database from our docs. So let me actually type an existing database. Let me call it Postgres. And since this is read-only, okay, doing this for now. So I've added a database right now. And I'm looking into the public schema. I have a bunch of tables here. So let me actually track, let's say, the products table, right? And let me go to the API to actually start querying. So we'll do like a GraphQL query, which says query products, and I get the ID, price, and like a bunch of details. If you look at the name, the timestamps, and whatnot. Let me also like limit the number of items that we actually get. And you can get back the JSON response, right, the way you asked for. And what's happening underneath is basically Hasura is connected to this Postgres database. It is tracked. We've explicitly asked it to track the products table to generate an API. And we've got a GraphQL API that we queried right now. We've executed it right now. And if we look at the Analyze tab, what's essentially is happening here is the compiled SQL that I was talking about, right? And we can see more examples of this in a while. Again, we're doing a slightly optimal SQL query than the naive SQL that you might have written, where you would have just said select star from products. You're doing a little bit of JSON aggregation over here. And you can look at the execution plan over here as well, right? Now, let's actually go ahead and track all the tables so that we get the APIs for all the tables. And this is again an existing database that you're looking at. Now, a lot of tables have foreign key relationships established. So let's also like track them so that we can query them in a nested relationship in a single query, right? So going back to the API, let me actually query, let's say the cards table. We have an ID.
So what you've done is you've kind of introspected the database to see what tables there are. The SQL itself gives you some sense of the relationship between the types or models there. And you're using that to, like you mentioned, generate the GraphQL schema itself, right? And
yeah,
Hasura, of course, is powering. Okay, got it.
Right.
Okay.
So all of this GraphQL queries, so you look at the docs, right? And this schema is already like automatically generated by Hasura after it introspected the database. And it has created a bunch of queries, which are pretty expressive. You have all the SQL benefits of like doing a var clause, order by, limit, offset, and other features and aggregate features on top of that as well, right? All of the schema and the queries on top of this is automatically generated by Hasura as soon as it was able to like introspect the DB and you allowed it to track an API on top of it, right? So
I get the richness of the SQL dialect that Postgres supports automatically in my API. So with this is I was able to see the where clauses that could have helped answer Dave's question if it wasn't business logic, if all you wanted was a filter, but understood.
Right.
That makes sense to me.
Right. Now I'm just making a simple query where just fetching carts and the list of cart items within that, which seems to be a relationship, right? Like a one-to-many relationship. One cart has many items. I've limited it to 10 items and I've gotten some data here. And let's look at an analyze here as well. And again, here, it's again a single SQL query that's being done. It might not look pretty from a readability point of view, but this is an optimal SQL, so to speak. And this is probably one variation of SQL that you will probably want to do it yourself, given a query like this, where instead of generating two SQLs and like going into the n+1 problem, or probably doing batching stuff on top of this, you might want to do a compiled SQL for this GraphQL query, assuming again, like you're talking to the database here in this case, right? So again, this is a pretty good SQL that's being generated, and we've benchmarked it for your reference. So again, this is again, you can do this for any levels of nesting. So I can probably also get in product ID, image of the product, and whatnot. So again, you can look at the relationship data coming in pretty quickly as well. So and it's pretty rich, as Sandy mentioned. You can do a where clause, and all of your pagination and filtering, all of that is totally possible. Pretty natural to think about how you will query SQL, but then just in a GraphQL interface, in a query interface, which also feels a little bit natural here if you look at this fetching relationships between them in one shot as a graph, right? So this is a pretty simple example to showcase what Hasura does on the compilation layer. I can quickly show what a GraphQL server looks like. This is a Polo server where I'm connecting to Postgres again, just getting a Postgres connection string here, setting up a few things, doing a bunch of type definitions and resolvers, right? And let's go into the type definitions. I'm just doing, like, I'm just fetching
Are
some
you
threads.
sharing your screen, Venture? I'm still looking at the Hasura console.
Yeah, give me one sec. I think it seems to be paused. Let me reshare. Give me one sec.
Demo cards are being kind to us today.
Yeah.
Barely are.
Are you able to see my screen now?
Yeah, I can see your screen. I'm seeing Visual Studio.
Right. Yeah. So I was just going to showcase a quick Node.js server example written in Apollo server for GraphQL. You have like a bunch. I'm just using an ORM links to connect to Postgres. I'm building a GraphQL server here. You typically write a GraphQL schema definition with types. So in this case, for example, I'm just doing a very simple type for threads, which has a couple of fields, and a query to fetch that data from the database, right? And a very quick resolver code, which is probably talking to the database here. So, and we look at the database query in the next step. So we have one query called threads. We have one resolver again for that to resolve this query. And the database query for that looks something like this, which is a naive select star from threads, limit, and whatnot. The problem with this is, of course, the context of this information does not tell you what fields were requested. It's not pretty easy to like filter out the number of fields requested by the client on the query. So for example, if somebody's asking for just the ID and not the created, it's pretty hard to filter it down to that result. There are some libraries that exist, which lets you do it a little bit better. PostGraphQL exposes a library which you can import and then filter it out. But typically, naive implementations just do a select star and then get it from the table. And what the GraphQL server does is, when before it returns the response back to the client, it filters out the objects which are not being asked by the client. So typically the filtering happens at the server side, but then you've already done the data fetching from the database, which was already unnecessary data from the DB. But yeah, this is the pretty simple one type definition, one resolver example. Now imagine this, imagine implementing like for 20 different tables in a database and different permutations and combinations for joins as well. Your type definition code will look pretty long. You would have defined all the types for all your tables, and also resolver code will not be as straightforward as this. As you start expanding here, you'll write a lot of SQL code, and then you'll start start optimizing this SQL that is being generated using an ORM here, but then again, you can compile your own SQL here again, right? So again, a lot of boilerplate code that you're gluing together and a lot of optimizations that you will worry about once you start expanding the scope of this GraphQL server that you're implementing. I have this server running on localhost here. What I'll do is I'll just quickly expose this publicly, and I'll just add this GraphQL server to my Hasura instance. So one of the teams in your organization probably is just using an e-commerce schema. They're just importing this. They have database access. They've added it to Hasura. They've got the API. There's another team probably which works on this custom GraphQL server, and you want to add that, right? So I will just say Apollo server, and I have this GraphQL API. I can forward all the headers here. What we're doing here is we're adding the GraphQL server that I just showcased, the custom GraphQL API endpoint, to Hasura. And now what Hasura does is it also merges this API into your schema. And so there are two subgraphs here right now. One is your Postgres one, which is just exposing database tables directly. And there's another one which is also indirectly talking to Postgres, but then exposing a couple of queries here, right? Now this API endpoint that you see here that Hasura exposes will actually aggregate both of your endpoints in both of your GraphQL queries in one place. Now I can start querying for threads, which was the query that I exposed on my custom GraphQL server. So you would have ID and created, and you get back a response from the database. This is the database that's running on my machine. So, and this is how you bring in your own logic incrementally into Hasura, right? And then you stitch together all your schemas into your stack. So Hasura becomes that super graph of sorts, which Sandy can quickly go over after this demo, where you are adding a bunch of subgraphs that different teams in your organization are working on, and add them and contribute to that one unified graph where all your APIs just merge into one place. And if you're working with Node.js, you can write your GraphQL server, which you typically wouldn't be doing if you're using a compiler approach. Once you do it, or if you already have one, you will just add them as a remote schema to Hasura and then incrementally adopting the API. What you typically will want to do is replace these resolvers that you've written that's talking to the database by actually exposing these tables in the database to Hasura, and then exposing an API directly on top of it. Because what it will also let you do is be very explicit about the query. Here, I haven't done anything more than limit. If I want to expose var clauses, pagination, sorting, and whatnot, this has to be a little bit more expressive here. I need to write a resolver which handles that in my database query as well. There's a lot of boilerplate code to write once you start getting the weeds of this. And quickly, I wanted to showcase an existing REST API example, and pretty standard Swagger spec example of a pet store. You have the Swagger spec. If you have a Swagger compatible API, you will have a spec JSON that you can typically reuse. And what I'll do here is I'll go and import from OpenAPI. And it has introspected this JSON. And let's say I just create this pet ID, right? What I'll do is I'll get this base URL for this. This base URL, and I'll just do a get request on top of this. An action has been created successfully. So what happened was I just converted a REST endpoint, which is OpenAPI spec compatible, into a GraphQL API. And what Hasura basically did was it introspected that API, converted the REST parameters into GraphQL types, your category, your status, your tags, and whatnot. And of course, you have the handler, which handles this endpoint. And let me actually go back to the query, and let's do a get pet ID. Let's probably do one. And let me see if there are more things that I can get. I can get a name, status, probably the tags and name as well. Cool, so I got back some data. And essentially, we just instantly converted an open API, compatible API into GraphQL. So now all of your APIs, your custom Node.js server, your Node.js Swagger spec API, your Postgres data, everything is now exposed into this one graph where you can now you can start querying from your front end or your client in one place. And you can also establish relationships between them as you go along in your use case of a super graph. But I'll leave it at this for the demo in the interest of time. And I'll quickly go. Yeah, Sandy, do you want to take this over?
I can do this. So folks, Praveen, thank you for the demo. First of all, I think as someone who may have had built a GraphQL API already, or I'm working with another team's GraphQL API, it was good to kind of see that I can save time in my future iterations. I don't need to throw away my existing work. I can make all of these things work together. I can start optimizing. I can start testing things and then see where things go, and then incrementally adopt more of this compiler approach. So that was great to see. And folks, so just building on top of what Praveen just demonstrated, right, which is what you're looking at right now, a subgraph architecture, which is Hasura in front of a data source, generating a GraphQL API, augmented with a lot of kind of production-ready features or API management features like caching, open telemetry, security, etc., to give you the confidence to expose this API to your client applications. You can go further and use Hasura in very mission critical architectures, which you will in most cases run into if you are deploying a reasonably interesting application to production. For example, one of the scenarios that we see very often is a data access layer or a common data platform. Lots of organizations have this problem of multiple domains, domain databases, microservices, and so on. So everything Praveen just showed you, multiplied that by the number of domains or domain teams that you have, and imagine the complexity of that problem of generating a GraphQL API over all of these domains. So you can use Hasura to do the aggregation, to do the federation over these multiple domains and present a unified GraphQL API to your client applications. And once again, kind of bolstered by stuff like caching, etc., especially if you're using some old databases. And speaking of, technology modernization is another kind of initiative that requires you to do interesting stuff like take your old databases or code and try to modernize them. For example, if you have a meaty MVC framework based code, old databases like DB2, and so on, and you want to start using modern databases like, I don't know, Aurora, Postgres, and start using React and so forth for your front end application. What you can do is you can do pipelines that take the data from your existing legacy databases, pump them into a new database, maybe of your choice, write your front-end applications in the new framework that you're interested in, and use Hasura to kind of instantly generate the backend APIs or the GraphQL APIs for it. So your modern stack is instantly available. Of course, you need to spend some effort, time and effort in kind of putting up these ETL pipelines and writing your business logic and maybe your front-end applications. But the overall process of moving from legacy stacks to modern stacks is super accelerated using something like Hasura. And on the same principles, if you're planning to move from your on-premise infrastructure to modern cloud infrastructure, public cloud infrastructure, you can once again use Hasura to first of all expose the data in your on-prem databases and business logic to client applications via Hasura running on public cloud infrastructure. And as you slowly migrate from, let's say, maybe a legacy database to a cloud provider's modern database, you can use some of the other architectures to iteratively make that migration happen. But long story short, Hasura works in a wide variety of production grade architectures that you need in production to to handle the kind of workloads and the constraints that you typically have in production. And we work very closely with users and customers as well. So if you happen to be an engineering organization that is grappling problems similar to these, please hit us up, and we'd love to work with you and find a solution for you that delivers on the promise of this compiler-based approach.
Yeah, thanks, Andy. Let's also look at some questions if there are any pending.
No new questions. Mike had a question about using column comparison operators. Mike, a couple of typos aside, I hope my answer takes care of that query. You can use column equals CQ comparison operators in Hasura's permission rules, not so much in the filtering in the where clause, but it's very easy to work around that by creating like a computed column or a field, and you know what to do there. Function computed
or
column,
probably functions like or store procedures, which again going back to the leveraging database that you want, and also like writing your own logic if you want.
All right. I think that's pretty much it. I see people dropping off because they, in all likelihood, have other calls. We have a few links here for folks who want to learn more. We have a community forum. We conduct office hours every week. So please feel free to join our Discord. Like Zach just mentioned, our office hours are at 10 a.m. Pacific time every Tuesday. That's actually now, if you join our Discord, you will see our office hours going on right now. Led by Tristan, and Praveen's soon going to hop over there too. So see you folks on Discord, I guess.
Yep.
Praveen, thank you so much.
Yeah. Thanks.
Thank you so much, folks, for joining us for this
folks
webinar.
on
And
Discord. Yeah.